as we move to fracking, particularly in the US, and also renewables in some places. But over the last couple of years, we've actually had a significant increase in carbon dioxide emissions. Now, what we've seen this year and what we're projecting for this year is a small decrease in those carbon dioxide emissions. We don't know for sure, but my suspicion is that it will be around about a 7% reduction, which shows up on this graph as a tiny little reduction, a little blip, the dashed line there. And you can see that compared with the big picture, what's going on in terms of coronavirus is actually relatively small in terms of emission reduction. So in spite of all the pain that we're suffering and the globe is suffering, is that the emissions are relatively unchanged, which is really quite remarkable, I think. And so the question here, I think, is whether we, after the coronavirus, whenever that might be, for whatever reason it might be, we could go into a trajectory which we might term snapback, which has been provided by some politicians, or we might go into a trajectory which is something like reframing or green recovery from this event. And really important to note that recovery, if we do it right, if we carry on this 7% reduction year after year, so 7% on 7% on 7%, that will actually be consistent with the Paris Agreement goal. So that's the 1.5 degrees goal. Is that if we don't, if we go back to the snapback, that goal will very quickly get out of our reach. It's already, I think, very difficult to keep temperatures to within 1.5 of pre-industrial. And if we do a snapback, it becomes virtually impossible relatively quickly. So the really important thing is that what we've seen, though, in terms of coronavirus is actually essentially reductions in emissions via behavioural change. Whereas to actually achieve the Paris Agreement goals, we need reductions in emissions by structural change. That's changing the way we deliver energy, the way we do transport, the way we produce our food, etc. So this is a bit of a picture of what's going on. And can everyone just make sure their microphones are on mute, because I'm still getting a bit of feedback there. So what happens in terms of carbon dioxide is that for every ton of carbon dioxide we put up into the atmosphere from sources like, coal-fired power stations and things, roughly speaking, a quarter of that gets absorbed by the oceans, a quarter of it gets absorbed by the biosphere, that's trees and grass and soils, and half of it sits in the atmosphere. And that adds to the half that was sitting in the atmosphere from the previous year and the previous year and the previous year. So it accumulates in the atmosphere because it is a very long-lived gas. Now, we actually do have a history of what this looks like in the atmosphere. So this is ice core data with more recent data from direct measurements from Mauna Loa and Cape Grim and similar places. But what this shows is over multiple ice ages, going back almost 1 million years, we can trace the carbon dioxide in the atmosphere. So Kiap, you've still got your phone on, so can you put it on mute, please? Still getting some noise coming from you. Thank you. And what you can see is that the Earth has gone through phases of increased carbon dioxide concentration in the atmosphere and decreases. So that corresponds closely with the glacials and interglacials. So when the carbon dioxide goes down, we're in a cold period of Earth's history. When it goes up, we're in a warm period of Earth's history, relatively speaking. And you can see the variation in that ranges roughly from 180 parts per million to 280 parts per million. But that translates to a temperature change in the Earth of about 5 degrees. And it relates to a sea level change of about 120 meters. So during the ice ages, sea levels, roughly speaking, 100, 120, maybe a little bit more meters below what it is right now. And so these changes in carbon dioxide are tightly linked to major changes in how our Earth system works, how our hydrology works, how our ecosystems work, etc. Now, on that graph, we're already well above that range, the natural variation between 180 and 280 parts per million. We're already sitting, roughly speaking, at 415 parts per million this year. It goes up and down with the seasons. That's why I say roughly. And we're heading towards the top of that graph on current trajectories. So This is a huge change in terms of a key driver of the Earth system. And we're adding to that year by year by year. And to give you a bit of a feel for what this means in temperature, I'll just give you this sort of global picture before we move into the Australian picture. And the reason why we think immediately of temperature is we've known for around about 150 years that if we put carbon dioxide in the atmosphere, we'll actually warm the Earth. So it was first hypothesized in the 1820s, then 1840s, first measured in the 1850s, first modeled in the 1890s, and everything since then has added to that understanding of the link between temperature and greenhouse gas concentrations in the atmosphere. Now, if we just look at this graph, before I kick this animation off, I'll just describe what it shows. This is a graph from a guy called Antti Lipponen in Finland. And what this shows is a global picture of temperature. So each of these little coloured dots down the bottom is a separate station, meteorological station. The colour coding indicates whether it's hotter than the long-term average in that station or colder than the long-term average in that station. They're arrayed from the southern latitudes to the northern latitudes, with the black line there being the equator. So you can actually see some geographical information in this. And the big sort of graph, the figure at the top, is the aggregate of all of those different stations. So compared with the long-term average at those different stations. So you can see that in the year 1900, that most of those stations were sitting around their long-term mean, but there were some which were about 2 degrees colder than the long-term average. There were some which are about 1.5 degrees hotter than the long-term average. So I'll just kick this animation off, and you can see what's happened year by year since 1900. Whoops, so we need to go back one. And so when we get to the most recent year on this graph, is that you can see not only has the average temperature changed, which is what we sort of generally talk about with global warming, but the really important thing here is the extremes in temperature have changed. And it's those extremes which drive biology, those extremes which drive our ecology and our ecosystems, and also those extremes which drive disasters and similar impacts. And so we've seen the average temperature or the modal temperature increase, which we'd expect under global warming, but really importantly, those upper end temperatures, places are now experiencing 5 degrees and more greater temperatures than they previously experienced. But some places are also experiencing 3 degrees lower temperatures than the long-term average. And so that temperature range, which I showed you before, which was roughly speaking about 3.5 degrees between the coldest place and the hottest place, is now about 8 degrees. So the temperature variability has massively exploded. So it's not just about average temperature increase, it's that temperature variability, which is really a critical part of the climate change story. And if we look at Australia, this is just a graph straight from the Bureau of Met website going back 100 years or so. You can see that there's this long-term increase in temperature right across Australia. Last year was by far the hottest year on record. And importantly now, almost everywhere in Australia experiences every year what would have in the past been considered a very hot year. So what my grandparents would have considered to be an extremely hot year is actually now pretty much normal, and it happens everywhere. So this is a message about there is no escape. There's no place you can go where these sorts of changes aren't impacting, and impacting seriously in Australia. And it's not only the high end of the temperature range, which is going up, as I mentioned in that wobbling jellyfish graph, but it's also the low end. So the frost risk in this case. This is work from Steve Crimp, who's looking at frost risk across southern Australia. And this is essentially, without wanting to go into detail because I haven't got the time, but essentially it shows a metric of frost risk. It's called a Goyne plot and it shows on the bottom screen temperatures going from 2 degrees, which is a light frost, down to -2, which is a heavy frost. And up the vertical axis is the last day of year of the 10th percentile of frost. So it's essentially how long the frost lasts, from year to year. So the sort of size of this polygon is sort of an indicator, a gross indicator of frost risk. So this is a polygon of frost risk for Wagga in the 1950s. And then I'll track through decade by decade. So it's the 50s, 60s, 70s, 80s, 90s, and year 2000s. And so you can see decade by decade, it's not just the high temperature risk that's increasing, but also the low temperature risk that's increasing. And this particularly impacts on biology through frost damage in crops, in viticulture, horticulture, etc. And just to sort of put this in a slightly different way, this is what I think of in terms of the operating environment that we deal with in terms of climate, in this case in Southern Australia. So what I've simply done here is taken the record from Southern Australia, plotted it out year by year, so each dot is a year, and it plots out rainfall versus temperature, so the average temperature for that year. And you can see that there's this relationship that hotter years are also drier years, and wetter years are also colder years. And there's a strong relationship across those different periods. Now, these are the years before 1950, and you can see I've just drawn an ellipse as a broad indicator of the envelope in which those temperature rainfall relationships operate. Now, if we split that record up to the pre-1950s, which is the blue ellipse, 1950s to 2000, which is the orange one, and post-2000, which is the red one, you can see that across these different periods, that relationship between temperature and rainfall is very, very robust. The slope of those lines is almost identical across those different periods. But when we actually overlay those ellipses on top of each other, we can actually see what's changed because of climate change, is that operating environment, which previously existed, say pre-1950s, almost now has no overlap with the operating environment we're experiencing right now. And within a few years, those will actually separate. And when that happens, we will be in uncharted territory. There is no precedent for dealing with the sorts of environment we'll be finding in those years ahead of us. And we can see from this graph that this is happening. It's happening right now, and it's extreme. So when we look at 2019 on this graph, we can see just how extreme our recent years have been in terms of this relationship. And this, of course, is impacting on systems right across Australia and right across the world right now. It's not an issue for 2050 or 2070 or anything like that. It's an issue right now and has been for quite some time. This is just one example of this. So this is work from ABARES, the Department of Agriculture agency, where they tried to separate out the technology and management signal from the climate signal in terms of farm profitability. And what they find is over big parts of southwestern Australia and eastern Australia, that climate impact on profitability has been severe already. So on average across Australia, it's already dragged down profitability by 22% across Australian broadacre farms. A few increases up in the north, but broadly, the message is negative for Australian agriculture. Of course, fire risk has also changed and also increased in Southern Australia. So this is a very recent paper by David Lindenmayer and colleagues. And what this shows on the graph is just area burnt in Victoria alone in millions of hectares, thousands of hectares in this one. And you can see that last year's fires, the Black Summer fires, were the highest on record. But, ever since about year 2000, those fires are becoming more and more extensive, not in every year, but the bad years are really bad compared with anything historically. And this is exactly what we expect out of climate change. So the fire season has grown, it's extended, days of fire danger, sort of high fire danger index have increased in frequency. The accumulated fire danger index has increased for pretty much every site across Southern Australia. The affected area has increased, and our controlled burning opportunities have reduced. So the window for cool season fires has actually shrunk. So there's there's a lot going on already in terms of fires. There's a lot already going on in terms of our oceans. So this is looking at the different sources of sea level rise. So this goes back in this particular graph, 1993 up to 2013. We can see that in 1993, the sea level rise was roughly speaking 2 millimeters per year. In this graph, it was up to about 3.2, but right now it's about 3.6 millimeters per year, and it's accelerating. It's not a linear change, it's actually accelerating over time. And really disturbingly is that if we go back to 1993, Greenland, the rate of breakdown on Greenland was contributing about 5% to that sea level rise. Right now, the estimates are well over a third of sea level rise is being contributed by Greenland breakdown every year. So things are happening, and they're happening really quickly, much more so than even a decade ago we would have predicted. Things are happening in terms of our oceans as well, in terms of currents and temperatures. So things like the East Australian current is moving further down our coast instead of heading off around Sydney to Jervis Bay latitudes. It's starting to move right down to Tasmania before it heads off to New Zealand. And that's bringing warm tropical waters and tropical species down to Tasmania, causing a whole stack of biosecurity issues and major ecosystem change around Tasmanian waters. We've seen changes in terms of our coral reefs already. So this is a graph from the IPCC. It's what we call a burning embers diagram, and I'll show you a few more in a few minutes. And that essentially is a color-coded risk diagram, white being no attributable risk to human climate change, moving through yellow, some risk, red, high degree of risk, purple, extreme risk. And if we look at what's happened to our coral reefs, if we go back to the 1980s, there was no reports of mass coral bleaching, either through, if we do coral cores, or through the oral histories of native indigenous peoples around the world. If we move to the 1980s, we start to see the first localized mass coral bleaching being reported. By the 1990s, it was the first global mass bleaching events. And by the sort of most recent years, we've seen back-to-back global mass bleaching events, which give the coral very little or no chance to recover following the previous bleaching. And so these are changes that are happening right now. They're also happening in terms of extreme events. So things like cyclones, there's more of them when we look at the global picture, and they're becoming more extreme. So more of the cyclones that occur are in category 4 and 5, the really extreme ones, and those wind speeds in those categories are also going up. That's the right-hand panel here. And not only that, they're spreading further south in the southern hemisphere and further north in the northern hemisphere. So places that used not to be affected by tropical cyclones now are being affected. So there's a whole stack of changes which are happening already under sort of about 1.1 degrees Celsius above pre-industrial. So the question then is, what's likely to happen in the future? So if we look at our emissions trajectories, which we may go down, they tell a very different story. So if we keep on doing what we've been doing recently, we go on the red trajectory, which leads us to a world 3, 4, maybe 5 or more degrees warmer than it has been historically. And to some extent, that's the current trajectory we're still on, notwithstanding the Paris Agreement. If we do everything, if every country said what they do under their current Paris agreements, we'd go onto this trajectory. And that would lead us to a world of 2, maybe 3, 3.5 degrees, and which is still very, very substantial change. And unfortunately, a lot of countries aren't meeting their current Paris Agreement commitments in terms of emission reductions, and including Australia. So we're not on the trajectory to get to 2030 emission reductions that we said we'd do. If we want to keep temperatures to 2 degrees, which is the main Paris Agreement goal, well below 2 degrees is actually the specific goal, or to 1.5 degrees, which is the Paris Agreement aspirational target, we've got to go either onto the blue or the dotted line trajectory. And you can see that the difference between where we're going, which is upwards to the right, and where we need to go to keep it to 1.5 degrees is massively different. And that's why I say, if we kept going with the 7% reductions that we've seen this year from this point down, but kept going 7% year after year, we could actually stay to 1.5. But at the moment, there doesn't seem the political will to do that. We have the technologies in many systems, but we don't have the political will to actually undertake that change. So what does this mean in terms of what the world might look like, say, in 90, 100 years' time? So these are graphs from the IPCC showing on the left-hand side the minimum temperatures, the nighttime temperatures. The right-hand side is the, sorry, it's the other way around. Left-hand side day, right-hand side nighttime temperatures, but under different scenarios of emissions. So on the top, it's low emission scenarios, sort of some of those lower curves that I just showed you. On the bottom, it's the high emission scenarios. And under those high emission scenarios, there's parts of the world, like up towards the Arctic, that might be 8, 9, 10, 11 degrees hotter than they have been historically. Around Australia, it's probably more in the sort of 4 to 5 degrees range, as I've just described. And people might say, well, that's pretty, you know, is it really serious that we're actually starting to see, you know, or going to see those sorts of changes? But just to point out that we've already seen temperatures in Australia, in parts of Australia, 2.5 degrees hotter than that long-term average. Up in the Arctic, we've already seen temperatures which are 11 and 12 degrees hotter than the long-term average. And in places like the Svalbard at Seed Vault, which is in the deep Arctic, where they never expected, even in a 100-year scenario, to have melted ice, it flooded a couple of years ago because the temperature was way beyond what they expected, and they had no flood protection in the Seed Vault. So these things are happening, and they're happening really quickly. And those temperature changes themselves will lead to massive increases in heat stress. So this is work from Antonio Mora and colleagues. Top left-hand side is historical heat stress. Bottom right-hand side is future heat stress, high emission scenario, end of century. You can see that across the top of Australia, pretty much every day becomes a heat stress day. Those sorts of heat stress conditions, which used to be affected places like Rockhampton, will stretch down to places like Canberra and Melbourne. So massive changes in heat stress, which will affect humans, it'll affect our livestock, it'll affect our ecosystems and the species in those systems. So heat stress is likely to increase. This study indicated something like over 75% of the world's population will experience multiple heat stress days in a given year by the end of the century. In terms of water, which is a crucial thing for Australia, major changes already and much more change heading our way. This is a graph of change in runoff. So runoff is what feeds our dams, feeds our rivers, etc., per degree warming. So this is what we call the median estimate coming out of the hydrological models coupled with the global climate models. You can see over in the southwest of WA, it's 25% per degree. Over in the Murray-Darling, it's 5 to 10%. So if, for example, we have a 3-degree scenario, we need to multiply these numbers by 3. So over in the west, it's 25% by 3, 75% reduction. Over here, it's say 30% reduction. Now, the worrying thing is that over in the west of WA, in say Perth's catchments, they've already had a more than 85% reduction in inflows into those dams. And over here in the east, we've seen something like about 20, 25% reduction due to climate change into our Murray-Darling inflows. And so, you know, rather than seeing these as extreme, in some ways they seem moderate. And if we look at the, in a sense, the best case scenario coming from the IPCC, so this is the wettest scenario, even in the wettest scenario, we can see there's substantial parts of Australia, in West Australia, South Australia, Victoria, which even under the best scenario have reductions in runoff. And the worst case scenario is grim everywhere. So over in the west, it's like 90% reduction for a 3-degree scenario. Over here, it's say a 60% reduction. And scarily, over in Southwest WA, they're pretty much already in this scenario in 2020. So, you know, very wise to take this very seriously because there's good reasons why we would expect to see reductions in runoff continuing as climate change goes on its merry way. And of course, this will make existing competition for water water resources much, much tougher in the future. Now, of course, it's not just about water, it's not just about fire, it's about lots and lots of things put together. And this is what we call a multiple hazard map, coming from, again, Antonio Mora. And this looks at drought and fires and heat waves, floods, storms, etc., and pulls it together in terms of one aggregate assessment of change in risk. And we can see that around the top end of Australia and through our region into the Pacific and Southeast Asia, South Asia, is in a sense the global hotspot for change in climate risk due to human activities. And so again, this is just something I think we need to take really seriously, because the implications, both domestically in terms of our environment and our society and our economy, are huge, but right across our region geopolitically, this is also potentially huge. Now, really, unfortunately, the more we know, the more concerned we get as a science community. So I showed you before what we call burning embers diagrams in the IPCC. So these are essentially risk diagrams, color-coded to indicate increasing levels of risk. So we first produced these back in 2001 in the third assessment report. And they were categorized into 5 different categories. So they were risks essentially to unique and threatened systems, particularly ecosystems, was one of the categories, extreme weather events, distributional impacts, risks of large-scale discontinuities such as breakdown of the Atlantic overturning circulation, similar things. And you can see that different types of categories of risk had different risk levels for a given temperature. So temperature is up here on the left-hand side, going from 0 to 6 degrees above the long-term average. So this was the picture in 2001 in the third assessment report, and I'll move through the subsequent assessment reports so you can actually see how the science assessment of risk changes. And so the third assessment report was like this. The fourth assessment report, you can see those red bars moving down as our knowledge base increased and our concern increased. The fifth assessment report, not only did those red bars move down, but we had to introduce a completely new category of risk, which was essentially extreme risk, which is largely unadaptable and irreversible. So that's the purpley sort of color there. Very similar to how we've included a new category of fire risk in our Australian fire danger signs. So this is the fifth assessment report. In the IPCC 1.5 degrees report, we repeated this, but these columns only go up to about 2.5 degrees. But again, you can see that moving down the sort of columns, the sort of red and purple colors. And so at a given temperature, our assessment of risk has increased progressively over time. And in the 1.5 degrees report, for the first time, we had enough data to start splitting this up into sectoral risks, such as warm water corals, which I've already shown you, coastal flooding, crop yields, tourism, etc. And what this shows is that there is no one size fits all in terms of risk. Depending on what sector you're interested in, there is a different risk profile from other sectors. And of course, these are really simplified aggregate versions of trying to get a global picture of something which might vary substantially on a local to regional basis. So GBR may be much more vulnerable than a coral reef in some other place, for example. So we're trying to start to, understand how this propagation of risk changes over time and how we portray that. So in fact, there's a paper which I'm a co-author on, which goes through the history of exactly what I've just showed you. And documents that well and looks at improving the process for doing this type of risk assessment. Now, the last one of these burning embers I'll show you is one for terrestrial ecosystems. So I've already showed you the equivalent for coral reefs there, which show even under 2 degrees, massive risk for coral reefs, warm water coral reefs across the world. And a similar thing happens for terrestrial ecosystems, but not quite as severe. So if you go back to sort of the 1970s, when we look at the data on climate change impacts, we couldn't really see a good climate change signal in terms of ecosystems. By the time we move forwards to today, you know, 1 degree, 1.1 degree, we're starting to see some impacts evident, particularly in places like alpine areas and you know, rainforests and things where there's drying impacts or fire impacts as well. By the time we get to 2 degrees, we're starting to get into the red zone, where there's very, very substantial changes which are widespread and very difficult to adapt to. And so when we sort of look in an aggregate way at our ecosystems, we're heading to danger territory, and we're heading there quite fast. If we look at the benefits and costs of this, so we're starting to get some more robust assessments of the economic benefits and cost of climate change. What's becoming very, very clear is that the costs of emission reductions and keeping temperatures down are really, really small compared with letting it rip and suffering climate change impacts out into the future. And so some work, particularly by Tom Compass down in University of Melbourne, has actually sort of tried to aggregate this just for about 6 different sectors, not the whole of the economy. And his numbers is that keeping temperatures down to 2 degrees, which is the Paris Agreement goal, versus 4 degrees, which is roughly where we're heading at the moment, is worth something like $17 trillion a year in the long run by the end of the century. And the other thing we've found out from those economic analysis is what is the true cost of, or at least estimates of the true cost of each tonne of greenhouse gas emissions. This is what we call the social cost of carbon. And there was a study a couple of years ago which brought together a whole stack of different methodologies to calculate this. And there was a lot of variance in terms of the final numbers between these different methods. But the median of those different methods was US $417 per tonne of carbon dioxide when you aggregate those impacts across the globe. So if, say, here in Canberra, we release a tonne of carbon, say through driving our cars to work, is that eventually that carbon dioxide gets distributed right around the world because it's a long-lived gas and a well-mixed gas. And that will impact on everywhere, like a farmer in Nigeria or a water manager in India or an urban dweller in the UK. And when all of those separate impacts are aggregated, some of them are positive, but a lot of them are negative, we come up with a median of $417. And just to think about that, we were sweating about a $20 a tonne Australian price on carbon. Yet the real cost of carbon is probably something closer to $600 a tonne. So we really need to start reflecting on what the real cost of what we're doing is and starting to take appropriate and rational action. Now, of course, what we always do in these circumstances is we change what we do, we adapt. And just a couple of slides on that because it's really important to give people some hope about these things. And so there is a lot of work going on in terms of climate change adaptation, both by practitioners who are adapting to the changes that they're seeing, but also in the research community and understanding how best to adapt and when to adapt and how to adapt and who adapts, etc. And the point I just want to make here is that when we start thinking about this, in the past, we've usually put climate at the center of this diagram. So everything is dependent on climate, everything starts from climate and climate change. And I actually think that's fundamentally the wrong framing. We actually need to start out with people and their values and their aspirations and the decisions that they make and work out through particular lenses of interest to perturbations in climate from climate change, etc., including, you know, other systemic changes that we're doing to the world. So you know, there's many other threats apart from climate change. But it's a really important framing to actually put people at the center and bring people's knowledge into the discussion about what they can do to manage climate change. And the other part that's really important is there's a tendency when you do that with stakeholders is to focus on the way things are. You know, so you end up doing incremental change to existing systems. And yet what I argue is that we need to think about the way things could be. And so we need to think about systemic change and transformational change, because if we don't do that, we actually may miss out on opportunities and we may actually maladapt by hanging on to what we've done for way too long. And we can see this already happening in our various systems. And so I think it's really important to think about systemic and transformational change as part of the planning process. And we tend not to do that very well in Australia. And just in one example of what transformational change might look like, this is a farmer up near the Queensland border, New South Wales Queensland border, called Peter Mailer. He comes from a long history of traditional farming, cropping and grazing in this region. I think great-grandparents moved in there in the 1800s. And he's actually started to doubt whether in fact that's the best thing. And he's trying moving into energy farming instead of traditional cropping and grazing farming. And this is a quote from him: "Solar farming is better money, safer money, easier money than farming, given the climate changes that they're seeing." And the really important thing here in this example is that he's adapting to climate change, but he's not just adapting by incrementally changing his system, he's introducing new elements to his system, and those elements actually address the core driving factor of climate change, which is those greenhouse gas emissions that I started out my talk with. So it's that integration of adaptation and mitigation activities that's really important and demonstrated by what Peter's doing. And there also is a tendency to just focus on the tech and ignore social and institutional adaptations, which often are really critical, and to address barriers to change, things that stop people changing, to build the capacity to change and to facilitate adoption so that good recipes for change can be propagated much more broadly. And if we're going to do that, we need to bring in stakeholders into the discussion. We need to co-design our innovations so that we bring their knowledge in. And oftentimes those stakeholders are the major knowledge holders in any change process, and they're the owners both of the change itself and the consequences of that change. And so we really need to think about them as part of the research team. And having said this, even the best adaptations that we can envisage adopted widely are not likely to take all of the risk out of climate change. So there will still be a residual risk from climate change, regardless of how well we adapt to this. Now, the last couple of slides just focuses on coronavirus and climate change and what we might be able to learn from the coronavirus pandemic that can apply to climate change. Now, a really simple starting point from this is you have to have some basis for thinking that this is a sensible comparison. So for me, there's a whole series of similarities. Both the virus itself and the carbon dioxide we produce and methane, they're invisible. We actually can't see them with the naked eye. There's lagged effects. So, touching a surface and someone else touching that surface and getting sick, there's a lag between those two things, just like there's a lag between our emissions of greenhouse gases and the consequences of those emissions. In both cases, there's an exponential element, exponential growth in cases for coronavirus, exponential growth in greenhouse gas emissions and its consequences. Both climate change and the coronavirus pandemic have personal implications through to global implications. Both of them have systemic impacts, right through our economy, and they require integrated responses. So the best responses are integrated, holistic responses. And both of them impact most on disadvantaged people. But having said that, there are differences. And one of those differences is that there is no constituency for the coronavirus to muddy the waters of public debate and to slow our responses down. Whereas very clearly, there is a constituency for fossil fuel emissions, etc., which unfortunately has those characteristics. So a few learnings from coronavirus from my take on this. Firstly, that early and informed action is good action. It may not be perfect, but it's likely to be good and point us in the right direction and help build momentum in terms of effective action. Secondly, uncertainty or huge costs. So huge uncertainty associated with coronavirus responses, particularly in the start of the pandemic, nor huge cost did not stop us from taking big decisions. And I would argue that we know a lot more about climate change than we did about coronavirus and still do about coronavirus, yet it didn't stop us from acting on the pandemic. but uncertainty is used as a way of stopping us from acting on climate change. We found that experts can actually be useful. And they're useful not only in terms of informing public health responses, for example, but they're also useful politically. So those political leaders who have actually taken on board expert knowledge and seen experts as part of the team to respond to this, their political stakes have actually gone up. Those who haven't, like President Trump in the US, their political stakes have way gone down. But it has raised for me, big issues about role creep. So people who arguably should stick within the science domain and the expert knowledge domain have started to push into the political domain, and that muddies the waters. So they should stick to actually informing the political decision, but letting our elected decision makers actually make the political decisions. And there's been a really interesting interplay across that, which I could go to at some length if necessary. We've also found that denial about these issues matters. So denial about coronavirus really matters. So there's an estimate that 1 week earlier, action by the UK could have halved the number of cases in the UK. And denial about coronavirus impacts actually resulted in increased cases. So denial really matters in terms of the pandemic, and I think it really matters in terms of climate change, as does inequality and disadvantage. So people who are unequal or have poor people or ill people are much more strongly affected by the coronavirus, just like they are with climate change. And coronavirus has demonstrated very clearly that effective response requires a shared responsibility. It has to be both an individual response and an institutional response working together. Neither by themselves is going to be enough to deal with the coronavirus. Neither by themselves is going to be enough to deal with climate change. It showed the significance of interacting risks, such as Cyclone Amphan, where the response to the cyclone actually increased the risk from coronavirus because of crowding in refuge centres. It's demonstrated the importance of good data so we can actually track and monitor and respond effectively, and integrated responses, so border management with medical management, with social security management, etc. And it's demonstrated that there are sensible recovery options that not only just take us back to where we were, but can take us forward to a better place than we have been. And I'm just running out of time, so I won't go into that. But there's been some really good work done by various groups. This is straight from Oxford University, a graph which shows how long-run benefits in terms of the economy can be very, very well aligned with long-run benefits in terms of climate change. And people like Frank Yotso in ANU and others have identified a whole range of policies that could be used as part of green recovery, which can respond to the economic and social disruption that we've experienced over the last months, but actually put in place things which are actually much, much better than what we've had in the past. And this includes R&D, includes natural capital investment, includes clean infrastructure investment. And at the moment, there's a huge problem in this in Australia because we hear stories about gas-led recoveries rather than starting to think about renewable energy-led recoveries. And we really need to change that dynamic so we can deal with the coronavirus and deal with climate change and deal with social inequities and improve our economy and improve our exports, etc., all at the same time. So there is a huge opportunity here. And at the moment, we're not grasping it. And at the moment, we're not responding to climate change in the way in which we need to, given the rates of climate change that we're seeing. Thank you.
Thank you for that, Mark. I really appreciate your talk. So if anyone has any questions that they would like to ask, feel free to add them into the chat, or you can also raise your hand under the participants bar. You should see a raise your hand option. So we'll wait around for any questions. we have a question from Peter. So, how do we convince the electorate that we need change? We need your lecture as a TV series.
Thanks, Peter, for that. There already a TV series on this, and you know, I really don't think, in a sense, that information is the limiting factor with climate change. So, if we look at multiple surveys, we see you know, high degree of alignment with us, you know, across Australia and other countries with action on climate change. So, for example, the last Lowy Institute poll, which has been going for many years now, showed that there was 90% of Australians wanted more action on climate change. That's 90. And it's quite extraordinary that you've actually got 90% of Australians agreeing on anything. And it's even more extraordinary that you'd have 9 out of 10 Australians saying they want something, and that there wouldn't be a political race to actually deal with that and to grab the votes that are aligned with that. So we have this extraordinary situation where the vast majority of Australians want action and they're not getting it.
I guess I would say in response to that, the Australian public aren't voting that way. And so now we're kind of getting to where Labor is arguing about reducing a lot of their climate change actions because they keep losing elections, going with very strong platforms versus the Liberal Party, which is a disaster.
Yeah. Look, I guess, Peter, we all have our own personal views on this one, and I certainly do. But it's true is that in the last election is that the vote didn't go down the pathway of the Greens and Labor, who had much stronger climate policies. But just because people want something doesn't mean they want something else more. And I guess it just comes down to a question of priority when people actually walk into the polling booth. What is it that they really most want? And it perhaps was just that the climate change because of narratives of uncertainty or because of you know, a view that this was a future issue rather than a current issue. You know, they just decided not to put that as high a priority as they may otherwise do. You know, for me, there's a few things that ideally would be great to happen. One of them is that we actually get a media who much more effectively portrays the balance of evidence and the information that people need to make good decisions, not just to acknowledge there's an issue, but to actually do something about it. We need to have a series of policies which actually make action easy rather than make action hard. And generally speaking, when people have two alternatives, you know, they look for the easy one. Is that you know, they don't want to necessarily you know, become activists on climate change, but a lot of them actually want to take action. So it's how do you actually make that action really easy, cost effective, and worthwhile for people, as well as allowing them to be seeing themselves as part of something bigger. And I think that there's a really huge demand for both leadership at the political level, but desire to be part of a bigger narrative here.
Awesome. So I believe Bernd has his hand up. So did he want to unmute and ask the question?
Thanks a lot. That was a great, though depressing presentation. I've got a question. You said something like COVID changed something like 7% in terms of emissions. So in some sense, you could argue it didn't cut the mustard. What we have done in our behavioral changes. So you know, we cut down aviation quite a bit, and that didn't help much. So what would be your recommendation? What would be the #1 behavioral change we should need to do, and would be the most effective one?
Yeah, thanks, Bernd. So when we actually look at our greenhouse gas emissions, airline flights, something like 2%. Our transport is around about 17 to 19%. Agriculture in aggregate is 29%. Industry about another third. Our coal-fired power stations another third. And so when you sort of add up all of these numbers, you've got big slabs of activity in places like Australia which really haven't changed at all under climate change. I mean, under coronavirus. So our food is still being grown and provided to our tables and exported. Our electricity demand has changed very little in terms of total. It's changed in terms of timing, where it gets delivered into homes rather than offices, but not in terms of the aggregate total. And so, and likewise, our industry by and large has continued on its merry way, etc. And so all that really remains is those behavioural changes associated with travel is the main thing that's changed in coronavirus. And as we, many places reduce the lockdown, that travel is bouncing back to sort of pre-COVID levels. And so these are relatively minor changes, and they're very temporary. And so to get really significant changes in terms of greenhouse gas emissions, we have to go for much more structural change. So it's moving from coal-fired power to renewables, which are both cheaper and more reliable than any new coal or gas system you're going to have. And so we need to think about structural change, not just relying on this little behavioural change blip that we've seen. And that also sends a really big message, is that a lot of the pressure in the media and in political discourse is about pushing down responsibility for things like climate change onto individuals. So it's your responsibility to reduce your meat consumption. It's your responsibility to turn down the thermostat or whatever, rather than accepting that there is an institutional and a policy responsibility as well. And so it's almost anything except dealing with this seriously and dealing with it in a policy context. So push it down to other people, lay the blame on individuals, don't do anything at a higher level. And ultimately we have to change that. And the big way of changing that is at the ballot box. And so I really do hope that next time around we see much better policies that everyone can actually vote on, and hopefully, ideally it would be bipartisan, so that these things don't come and go with political swings and roundabouts.
Awesome. And I see Ben Kifford has his hand up as well.
Yes, hello. I just want to ask a couple of things. First of all, the analogy between COVID and climate change, in particular the lag, is one really critical difference, because with COVID, the lag is days or maybe weeks. And with climate change, even though effects are happening now from climate change, any action done now is going to be years or possibly even decades until the outcome is seen in the climate, in terms of change from today, not change from historical levels. So, and particularly with politicians elected on 3-year cycles and so on, then that's a huge difference, because for their political career, they effectively don't have to worry about the outcome of it in terms of being elected. While with COVID, they're going to find out within, days or weeks of making a decision or not making a decision, and that's really critical.
Yeah. Thanks, Ben. And you're quite right. The learning cycle from action to consequence is much shorter from coronavirus, and that is part of why and how we've responded so quickly. In a sense, it's true about climate change, but not true. So when we emit some carbon dioxide from our tailpipe of our car, that immediately starts changing the radiative balance. It doesn't hang around in the atmosphere for 10 or 20 years before it starts changing the radiative balance. It does that straight away. It's just that the cumulative effect of these is what we're seeing within the climate and the system.
A politician who's interested in votes at the ballot box, that's their so if tens of thousands of Australians started dying from COVID virus, then that political power which didn't implement things, you could expect that they would be voted out very quickly. So
absolutely,
it's what they're interested in.
Yeah, and that's right. And so and I acknowledge that, and I said that that's a big difference there. But I would actually also say that there is a difference here, and that is the COVID response, that learning curve, is actually driven by empirical understanding. If you don't do personal separation, personal distancing, you're likely to get coronavirus, and the cycle there empirically is dealt with very quickly. That's a pretty dumb way of responding to a system when you actually have a theoretical understanding of the system already, and when you have a lot of past experience that demonstrates the linkage between an action and a consequence. And that's very much true with climate change. So if we just want to approach this on an empirical basis between, you know, an action which emits greenhouse gases and a consequence, we're always going to be way behind the 8 ball when it comes to climate change. But we don't have to do that because we have other sources of understanding which we have in the bag right now. And if we ignore those, why would we bother doing science?
Well, I suppose, so we largely have ignored those up until now.
Not everyone. And so politically, we have in Australia, but we are outliers. If you look at Australia versus the rest of the OECD, we are gross outliers halfway towards where the US, which is even a bigger outlier. And there's other countries and other groups of countries which have taken this much more seriously, and they are doing well because of it.
Mark,
Hey,
just a quick question. Sorry. Just a quick question. The big elephant that's always in the room, of course, is human population growth. Do you see that as a long-term strategy that we also need to be looking at? I mean, we can try and get these CO2 levels down as fast as we can, but ultimately, you know, with the population continuing to grow exponentially, then we're sort of, it's one step forward, 2 steps back.
Yeah.
You know, because there'll always be a need to emit some CO2. Just,
yeah.
You know.
So it's a really interesting question, Ken, and there's very different viewpoints on this depending on, you know, values of individuals and values of nations, and it's long been a very contentious area in international negotiations, and there were particular events which drove that at the moment. In my view, there is absolutely no question that if we pull back on population growth in Australia, which is largely driven by immigration, but not only, it makes it much easier to meet any given emission reduction target. Is that, you know, having a population of 28 million is going to make it that much easier than if you have a population of 38 million. And that's, in my view, not, you know, it's so obvious, it's very hard to argue with. But emissions are a function not only of population numbers, they're a function of how we live. You know, we live very well in Australia, and also the technologies we use, whether we drive petrol-driven cars or electric vehicles, and whether we have coal-fired power or renewable power. And so there's many other elements to emission trajectories than just population. And I would argue that we probably need to move on all of those things. We don't want to sacrifice necessarily our standard of living, but nor do we want to prevent people, say a farmer in India, from aspiring to a better standard of living, something akin to what we have. And so there's big issues about equity that come into play here. And it's about finding pathways where we can actually have more prosperity, where we can have better educated people, and where we can have good environments at the same time. And the really important thing about that is that what decades of experience have shown us is that in terms of population control, the 2 best things are women's education and prosperity, particularly prosperity for women. So it's actually, you know, the enabling environment that so they can make their own decisions in terms of their you know, fertility, their family planning, etc. And that's the thing that's going to cap populations in the long term, is actually looking after other people.
Thanks.
Okay, thanks very much for the questions, and we might wrap it up there. So Mark, thanks a great deal for a great presentation. I think there's a lot in there to be positive about, and we look forward to hearing more about your work and the IPCC in the future, and hang in there, and we greatly encourage you to continue. So thanks very much.
Absolute pleasure. Thanks, Libby, and thanks, Jim.
Thank you.
And thanks for all your questions too. Sorry I couldn't get to them all.
Thank you, everyone.
Thanks again.
Cheers. Bye.